Hello guys, welcome back. So in this part, we want to discuss the next topic, that is Quadrature's law. We already said it that Quadrature's law used to describe the properties of a weak electrolyte, or describe the conductivity or molar conductivity of a weak electrolyte, right? Yeah. So Quadrature's law of independent migration of ions, otherwise said to be Quadrature's law of independent migration of ions. Okay. So Quadrature's law states that we know limiting molar conductivity, the molar conductivity at zero concentration, or molar conductivity at infinite dilution, or the maximum value of molar conductivity, right? Yeah. So that limiting molar conductivity of an electrolyte, we know that every electrolyte, let I have an electrolyte AXBY, how it get dissociated? It dissociated into XAY plus YBX minus. How can I dissociate this salt into XAY plus and YBX minus? We know that this is a compound of A and B. Ready? With the valency of A written in the top of A. Valency of A written in the top of A, let it be Y. And valency of B written in the top of B, let it be X. Ready? Then by interchanging their valency, we can formulate the formula, chemical formula. I think you are familiar to formulate the chemical formula for molecule using valency, right? So it is clear that if I have a compound like AXBY, the X term indicates that it is the valency of Y. Valency of the opposite component, right? Something which below a component which indicates the valency of the complementary component, right? So X is the valency of B, whereas Y is the valency of what? Valency of A. Okay, which means if I have a compound like this, Al2O3, then the 2 is the valency of O, 3 is the valency of aluminum. Okay, so how can I split this into 2 or this into XAY plus YBX minus? That you have to know first. Okay, listen here. AXBY may split it into A plus B, right? No doubt. If it undergoes a dissociation, then there will be A and B. Agreed? How much A? The molecule said that have XA and YB. So, no doubt, there will be XA. There will be XA. And how much B? There will be a YBs. No doubt. Ready? Then we want to show the charge of each substance on the top, right? Yeah. What do you mean by the oxidation state? It is a charge or valency, right? So let me write the oxidation state of A here and B here. For that, I want to know the valency of A. How I get the valency of A if I have the molecule? That is already discussed, right? Yeah. Valency of A will be below B, right? Or this subscript of B, right? So valency of A will be Y. So this is Y. Since it is a cation, Y plus. And valency of B will be just below the A. X. Since it is a cation, anion, this is X minus. This is how you can split the salt into 2. Okay. I'll give you some examples. Listen. If I have NaCl, no problem. It's splitted into NaCl. How much Na? 1. Because here is 1. How much Cl? 1. Because here also 1. What is the valency of Na? That all we know, plus, and Cl, that all we know, minus. And AlCl3. It's splitted into Al plus Cl, right? Yeah. How much Al? Only 1. How much Cl? 3. What is the valency of Al? That is in the that is below Cl. 3. 3 plus. Valency of chlorine below Al. -1. So this is how you can split. Okay. The next Al2 SO4 thrice. So this may split it into two categories, such as Al and SO4. The valency, how much Al? 2. How much SO4? 3. Valency of Al will be just below SO4 2 minus 3 plus. SO4 valency will be just below Al 2 minus. Is it okay for you? I'll give you one more example. Zirconium phosphate. So this is splitted into two, zirconium and phosphate. Ready? The valency of zirconium, just how much zirconium? 3. How much phosphate? 4. Valency of zirconium just below phosphate, 4. 4 plus. Okay, and the valency of phosphate, PO4, just below zirconium, 3 minus. So it is okay for you? Fine. So this is how you can split an electrolyte. Okay, and this is very useful in your Cold-Ratius law, and moreover in your solubility product of equilibrium. In ionic equilibrium, there is a section of solubility product. Okay, where we require this. Fine. Okay. Listen here. Listen. So let me define Cold-Ratius law. So it is very clear that an electrolyte have cation and anion, right? Every electrolyte have ions as cation and anion. Agreed? Yes. Then every electrolyte has ions of cation and anion. Fine. So Cold-Ratius law states that the maximum molar conductivity of this electrolyte, maximum molar conductivity offered by this electrolyte will be the sum of molar conductivities of its constants. Sum of molar conductivities of its constants. The maximum molar conductivity is otherwise known as limiting molar conductivity, right? Yeah. Limiting molar conductivity. The maximum molar conductivity, the top molar conductivity, which means the molar conductivity at 0 concentration, is otherwise known as limiting molar conductivity. So limiting molar conductivity of an electrolyte. So if you want to find the limiting molar conductivity of an electrolyte, then it will be the sum of limiting molar conductivities of its constants. Constants are what? What is the constant of an electrolyte? Cations and anions. So it is the sum of limiting molar conductivities of cations and anions. Ready? So it is very easy concept. We know that electrolyte have cation and anion. So in order to find the molar conductivity of an electrolyte, or the maximum molar conductivity or limiting molar conductivity of an electrolyte, you simply find the molar conductivity of its constants, such as molar conductivity of cation and anion, and have a sum up and make a sum. Ready? Then you obtain what? A molar conductivity of that electrolyte. Okay, so that is said to be Cold-Ratius law. Listen here. Limiting molar conductivity or equivalent conductivity, limiting molar conductivity or equivalent conductivity of an electrolyte will be the sum of limiting molar conductivities of its constituents. Sum of limiting molar conductivities of its constants. Whose constants? Electrolytes constants. What are they? Cation and anion. These all are the constant, no doubt. Ready? Okay, listen here. So, according to Coleridge's law, if I have an electrolyte AXBY, we know that it can split it to produce AY plus cation and BX minus anion. Okay. Moreover, there will be XAY plus cation and YB minus anion. Okay. So, let me write the Coleridge's law expression for molar conductivity of this electrolyte. Lambda M0, limiting molar conductivity of the electrolyte AXBY. What it is? Limiting molar conductivity of the electrolyte AXBY. This will be the limiting molar conductivities of the cation. What is a cation? AY plus into number of cations. So, in order to find the limiting molar conductivity of that electrolyte, you simply choose the limiting molar conductivity of your cation into lambda m AY plus into number of such AY plus. How much? X plus to find the limiting molar conductivity of the anion. What it is? Bx minus into its number. Ready? Fine. So this is the expression for limiting molar conductivity of an electrolyte. Whereas the limiting equivalent conductivity of the very same electrolyte will be written as limiting equivalent conductivity of that cation, plus limiting equivalent conductivity of that anion. This is enough. No need of multiplying with the numbers. For equivalent conductivity, you simply add the limiting conductivity of cation and limiting conductivity of anion. This is enough. Ready? For equivalent conductivity, you simply add the limiting conductivity of cation and limiting conductivity of anion. This is enough. No need of multiplying with the numbers. Okay? See the difference. If you are given with the limiting molar conductivity of cation and limiting molar conductivity of anion, in order to find the limiting molar conductivity of that electrolyte, you simply take the limiting molar conductivity of cation into how much cation plus limiting molar conductivity of anion into how much anion. That will be the limiting molar conductivity of that electrolyte. But if you are able to find, or if you are asked to find limiting equivalent conductivity of that electrolyte AXBY, okay, then you simply choose the limiting equivalent conductivity of cation and limiting equivalent conductivity of anion and make a sum. No need of multiplying with any other kind of numbers. So here the caps lambda represents electrolyte and the smaller lambda represents the constants. Okay, fine. Listen, I'll give you example. Listen. If I have electrolyte Al2O3, ready, and it's lambda m, and listen, lambda m Al3 plus is given in the question as X. Lambda m O2 minus is given in the question as Y. Moreover, lambda E of what? Al3 plus given as P. Lambda E of O2 minus, let it be P, Q. And you are asked to find a limiting molar conductivity of that electrolyte. What is electrolyte? Al2O3. So in order to find the limiting molar conductivity of that electrolyte, first of all, you have to split this category. If it undergoes a dissociation, there will be Al and O. How much Al? 2. How much O? 3. What is the valency of Al? That is just below your O. This is okay. It is already discussed in the first section, right? Listen here. So we know that Al2O3 splitted to Al3 plus and 2Al3 plus 3O2 minus. So I want to find the limiting molar conductivity of Al3 plus. First of all, I want to choose the limiting molar conductivity of cation. These all are small lambdas, right? Yeah. Whatever it may be, smaller caps. Simply the meaning is limiting molar conductivity. So limiting molar conductivity of that cation into number of cation. Yeah, 2. Is it okay? Like limiting molar conductivity of anion into number of anion. Is it okay? Whereas in the very same time, if you are asked to find limiting molar conductivity of limiting equivalent conductivity of electrolyte Al2O3, and you are given with the limiting equivalent conductivity of Al3 plus. So there is no need of multiplying with the 2. Ready? Because the limiting equivalent conductivity is given. So you simply sum up these two. See the difference? Okay. But now my question is changed. Listen here. Listen carefully. See the difference. So this equation, the boxed equation and this concept is okay for you, I think. If you are asked to find limiting molar conductivity of an electrolyte and you are given with the limiting molar conductivities of constituents, then what do you have to do? You simply pick the limiting molar conductivity of cation and multiply with the number of cation plus limiting molar conductivity of anion and multiply with the number of anion. Whereas within the same time, if you are asked to find the limiting equivalent conductivity of an electrolyte and you are also given with the limiting equivalent conductivity of constituent, so you simply choose the limiting equivalent or pick the limiting equivalent conductivity of constituents and simply make a sum. No need of multiplying with the number of cations or anions. Okay, ready? Now the question is turned. Now the question is changed. How we can do this? Listen here. Now my electrolyte is Ca3PO4 twice, calcium phosphate. Okay, let me check how we can split into 2. I'm sorry, this is the expression, right? Yeah, and the values are given in terms of xy. So limiting molar conductivity of these all are limiting. Okay, so lambda 0 is needed. Limiting molar conductivity of Al3 plus is x, so x into 2. Like limiting molar conductivity of O2 minus is y, so y into 3. So this answer will be equal to 2x plus 3y in a general format. Here, limiting equivalent conductivity of Al3 plus is P and limiting equivalent conductivity of O2 minus is 2, PQ. So this is just P plus Q. Fine. And here the values given as, limiting molar conductivity of Ca2 plus given as x and limiting molar conductivity of PO3 minus as y. Okay. But you are asked to find the limiting equivalent conductivity of Ca3PO4 twice. That is the difference. You are given with the limiting molar conductivity, but you are asked to find limiting equivalent conductivity. But this is not the case. Here, limiting molar conductivities of constants given and limiting molar conductivity of electrolyte is asked. Limiting equivalent conductivity of constants are given, limiting equivalent conductivity of electrolyte is asked. But here, limiting molar conductivities are given, but limiting equivalent conductivity is asked. Then how can we do that? For anything, before the calculation, simply let me split this into, let me dissociate this electrolyte, okay? So Ca plus P of O, right? Yeah. How much Ca? 3 Ca. How much P of O? 2 P of O. What is the valency of Ca? It is 2. 2 what? 2 plus. Because just the bottom of your P of O. What is the valency of P of O? That is 3. 3 minus. Because the valency of P of O will be here, right? Yeah. Fine. Listen here. So, what is a simple expression? Limiting equivalent conductivity of CO3 P of O2 minus means, what is a cation? Ca2 plus. What is the anion? P of O2 minus. So, I need the value limiting equivalent conductivity of the Ca2 plus and plus limiting equivalent conductivity of what? P of O3 minus. This is enough for me, but the value is not given. Limiting equivalent conductivity is not given, but limiting molar conductivity is given. Here is the logic. I already discussed that limiting molar conductivity divided by limiting equivalent conductivity is equal to normality divided by molarity, which is equal to n factor. Do you remember it in the previous section? Yeah. So that is a relation. Molar conductivity divided by, for a particular electrolyte, if it's molar conductivity divided by equivalent conductivity, the answer will be equal to n factor. Answer will be equal to n factor. Is it okay for you? Is it okay for you? Yes. So, if I have limiting molar conductivity and I want to find limiting equivalent conductivity, what is the expression? This to here and this to the bottom. Limiting equivalent conductivity is equal to limiting molar conductivity divided by n factor. So I need the limiting equivalent conductivity of Ca2 plus, but I have limiting molar conductivity of Ca2 plus. So limiting equivalent conductivity of Ca2 plus is equal to limiting molar conductivity of Ca2 plus divided by n factor is the relation. So limiting molar conductivity of Ca2 plus, let it be the limiting molar conductivity of Ca2 plus. Oh, now the value is given, right? Yeah, the value is given in the question as x. Ready? Fine. Oh, simply, this is enough now. In next step, I can replace it, okay? Limiting molar conductivity of Ca2 plus divided by, what is the n factor of Ca2 plus? For a cation, I already said it in your redox reaction. For a cation, the n factor is number of positive charge, that is 2. Just very same time, I want to find limiting equivalent conductivity of P of O3 minus. If I have limiting molar conductivity of P of O3 minus, then I want to divide it with n factor. So that is limiting molar conductivity of P of O3 minus. The n factor of this species, no doubt it's anionic charge, that is 3. So now it is okay. I got limiting equivalent conductivity of Ca2 plus as limiting molar conductivity of Ca2 plus divided by 2. So here, limiting molar conductivity of Ca2 plus divided by 2 plus, tell me, limiting equivalent conductivity of P of O3 minus in terms of molar conductivity. Limiting molar conductivity of P of O3 minus divided by 3. So, this will be equal to x by 2 plus y by 3, right? Yeah. Limiting molar conductivity, x, so x by 2. This is given as x and this is as y in your question. So if I am crossing this one, what happens? It will be 3x plus 2y divided by 6. 3x plus 2y divided by 6. 3x plus 2y divided by 6 will be the limiting equivalent conductivity of Ca3 P of O twice. Ca3 P of O twice. Is it okay for you? Is it okay for you? Or we can do another method. We can do another method. What is that method? Listen here. The values given is limiting molar conductivity, right? But you're asked to find limiting equivalent conductivity. Agreed. So, first, in order to find limiting equivalent conductivity of CA3PO4 twice, PO4 twice is, CA3PO4 twice, you want to find limiting equivalent conductivity of CA3PO4 twice. Okay, so for that, you first find the limiting molar conductivity of CA3PO4 twice, and you divide it with n factor, right? This is also useful. Limiting molar conductivity divided by limiting equivalent conductivity will be n factor. So if you want to find limiting equivalent conductivity, you pick the limiting molar conductivity of that particular substance and divide it with n factor. So it is clear that for a salt, I already told you in redox reaction, for a salt, what is the total positive charge or what is the total negative charge? That will be the n factor, right? Yeah. So the salt is CA3PO4 twice here, right? Yeah. So what is the total positive charge? The charge of calcium is +2, all we know. So into 3 calcium. So the total positive charge is +6. No doubt, the total charge will be, negative charge will be -6. Then only it will become neutral, right? So here in this question, I want to find the limiting equivalent conductivity of CA3PO4 twice. And this is one of the method. Or another method is that, what do you find? Limiting equivalent conductivity of CA3PO4 twice. So you simply, first of all, you simply find limiting molar conductivity of CA3PO4 twice and divide it with the n factor. Divide it with the n factor. Ready? Fine. So what is the n factor here? The total number of positive charge or total number of negative charge. So divided with 6 is the meaning. So let me find the limiting molar conductivity of that electrolyte. Limiting molar conductivity of electrolyte means limiting molar conductivity of CA3PO4 twice is equal to the limiting molar conductivity of Ca2 plus into how much Ca2 plus 3 plus limiting molar conductivity of PO4 3 minus into how much PO4 3 minus 2. We know that if it is limiting molar conductivities, then you should multiply it with corresponding number, right? And the limiting molar conductivity of Ca2 plus is given in the question as X. So X into 3 plus limiting molar conductivity of PO4 3 minus is given in the question Y. Y into 2. So this is equal to 3X plus 2Y. What is equal to 3X plus 2Y? Limiting molar conductivity of CA3PO4 twice equal to 3x plus 2y. Okay, so this value is equal to 3x plus 2y. Therefore, limiting equivalent conductivity of CA3PO4 twice will be limiting molar conductivity that is equal to 3x plus 2y divided by n factor that is equal to 6. So what is the logic? These two are same. These two are same. So in what sense, whatever be the sense, the answer will be same. So this is the idea. Got it? So I'll refer you to do in this fashion. Okay. So you simply find the values. Ready? Find the values. First, you simply check that which values are given, whether it is limiting molar conductivity or equivalent conductivity. If it is limiting molar conductivity, we can easily find the limiting molar conductivity of electrolyte. So first of all, you have to find or you have to check that which values of the constants are given. Limiting molar conductivity or limiting equivalent conductivity. Yeah. Here in this question, limiting molar conductivity is given. So, if limiting molar conductivities of constants are given, you can simply very easily find limiting limiting molar conductivity of that electrolyte like this. And once you obtain the limiting molar conductivity of electrolyte, you can simply convert it into limiting equivalent conductivity, provided that you simply you can use the support of n factor. So this one is more better because this may take a lot of time. Okay, I'll give you the reverse version of this one. What it is? Here I give you, or I given you the limiting molar conductivities, and I'm asked to find limiting equivalent conductivity. Now I'll give you limiting equivalent conductivity, and I'm asked to find limiting molar conductivity. So the best method is which values are given and what you can find directly, then calculate it. Finally, you convert into molar or limiting equivalent. So I have an electrolyte Al2 SO4 thrice, ready, and the limiting equivalent conductivity of Al3 plus given as A, limiting equivalent conductivity of SO4 minus given as B. But the question is, you're asked to find the limiting molar conductivity of Al2 SO4 thrice. Limiting molar conductivities of Al2 SO4 thrice. This is a question. It's very easy. Here the components are what? Limiting equivalent conductivities. So, which component is given equivalent conductivity? So, from that you can easily find limiting equivalent conductivity of that electrolyte, right? Yeah. How it is? For if equivalent conductivities are given, how can we find the equivalent conductivity? You simply add the equivalent conductivity of that electrolyte, right? So equivalent conductivity of Al3 plus equivalent conductivity of SO4 minus. What are these? A and B. No need of multiplying with the numbers. Yeah. So from the given data, I can easily find the equivalent conductivity of that electrolyte. But I want to find the molar conductivity. How can we find the molar conductivity if equivalent conductivity is given? We know that molar conductivity divided by equivalent conductivity is equal to n factor. So if you cross the equivalent conductivity into the equivalent conductivity in n factor is equal to molar conductivity. So if you want to find molar conductivity and you are given with the, or you are able to find equivalent conductivity of that electrolyte, then you simply multiply it with the n factor. So this value I'm already find A plus B, and this have to multiply with the n factor. What is n factor of this salt? N factor of this salt will be total number of positive charge. The charge of aluminum is plus 3 and number of aluminum is 2. So total number of positive charge is 6. So the n factor is 6. So this one will be 6A plus 6B. Okay. So this will be more better, I think. This way will be more better. Or we can also do it in another fashion. Right. How we can do that? How we can do this question? Molar conductivities are asked. So what is the expression? Limiting molar conductivities of component Al3 plus into number of Al will be 2 plus limiting molar conductivity of SO4 minus into number of SO4 minus is 3. But I want to find this value in the question. Limiting equivalent conductivity is given. So limiting equivalent conductivity of Al3 plus into n factor of that substance, that is 3. That is into 2 plus limiting equivalent conductivity of SO4 minus into n factor of that substance, that is 2 into 3. So finally the answer is very same. 6 into this value. This value is A plus 6 into this value is B. In both cases the answer is same. Okay. So you can choose which method is better. I'll refer this method. What? Which values of constants are given? Molar conductivity or equivalent conductivity? Then you find the corresponding value. If equivalent conductivities of constants are given, find equivalent conductivity of electrolyte. Or equivalent conductivity, molar conductivity of constants are given, find molar conductivity of electrolyte. Finally, you convert the molar conductivity into equivalent conductivity and equivalent conductivity into molar conductivity using n factor relation. Ready. So anyway, this is called Rashid's law. And this is a relation between nickel conductivity and molar conductivity. I think you are okay with this, okay? And let's do some problems. Before that, there is one more type of problem like this also. If lambda m0 of KCl equal to x and lambda m0 of NaCl equal to y, then find lambda m0 KBr minus lambda m0 NaBr. This is called Rashid's law. It's very easy. And we all know that KBr split into K plus Br minus and NaBr split into Na plus Br minus. So what is the cold Rashid's law expression for this electrolyte? Lambda m0 of K plus lambda m0 of Br minus of, tell me, lambda m0 of Na plus lambda m0 of Br minus. What will be the final result? This minus of lambda m0 Br minus and this one will cancel, and the final result will be lambda m0 of K plus minus lambda m0 of Na plus. So we should find this value. What is the value of lambda m0 of K plus minus lambda m0 of Na plus? But you are given with this value. Okay, so very easy. What it is? Lambda m0 K plus lambda m0 Cl minus is x. What about this one? Lambda m0 Na plus lambda m0 Cl minus is y. Then if you are lessing 1 minus 2, this one may cancel. Then what about this one? Lambda m0 K plus lambda m0 K plus minus lambda m0 Na plus, and this gets 0, and this one will be x minus y. So exactly this we have to find. So right, so this answer will be x minus y. So that relation is simply find from your cold Rashid's law. So questions like this may also ask, and there is 3 important applications for your cold Rashid's law. Let's move into that.